Thank you. Can you hear me okay?
Yeah.
Just checking initially, of course. So hello everyone, my name is Pierre Missionabier. I'm working with the Hermod team at INRIA in France. And today I will, as was first already said, talk about how to use virtual machine level tooling with language level ordinary object pointers. So in this talk, I will differentiate between the language level and the VM level. What I consider to be the language level is Java, for example. So at the source level, I'm writing Java code, and then this code um, is processed and provided to a virtual machine. So in the case of Java, that's usually your hotspot, G9, JXRVM, Maxine, or any other JVM. I'm also adding here Pharo in the source at the source level and the Pharo VM at the virtual machine level, because this is the environment in which I did my experiments. So the thing is that at the language level, we have a lot of tools. We have debuggers, profilers, compiler, code browsers, testing frameworks, refactoring, so many tools everywhere for everything. We can do many, many things. But as soon as we switch to the virtual machine level, we have a lot less tools. We have also debuggers and profilers similarly than we have at the source level, memory visualization as well, and Bootstrap in some cases. In the case of Pharo specifically, we have very little tools. We have actually two tools, and none of them concern Pharo developers. And I want to give you an example of why this is important that we know and are able to do some tools at the VM level with this small example. We had a student in our research team at some point that was trying to evolve the Pharo graphical user interface, which is written in Pharo itself, and therefore she added a breakpoint inside this method in the class form. She worked around, tried to do some stuff. Okay, it works, good. And at some point, she saved and went on to do something else. And when she came back, actually, this was broken. The environment didn't say anything anymore. Nothing was working, and she asked if someone had an idea about how to help her. And the thing is that when we move on to the command line, we get a debug stack which gives us our method, sorry, the breakpoint. And actually, what that means is that we are frozen inside that state of waiting for a user action. And the thing is that what happened is that the Pharo environment tried to start up, but was couldn't because it was stuck inside this breakpoint. And the thing is that in the Pharo environment, you cannot fix that. This meant that our work was lost. So to solve this issue, we needed VM level support. So uh, let's try to code the VM level tool then. And the thing is that in Pharo, we have two VM. We have a production VM, which is used by all of the users, and the simulated VM, which is written in Pharo, and which can execute the same code as the production VM. This code is usually in a memory snapshot. So this is a memory dump, basically, that we upload back in the RAM, and that we treat as via our environment. And this is usually a very big byte array, and like this one was about 100 megabytes. And okay, I found the class form here, but actually that's not the class form. That's just the string of the name of form somewhere inside this binary. So this is of course very difficult to work without the VM simulator. So VM simulator is already a good tool, and the VM in general is manipulating ordinary object pointers. An ordinary object pointers, or OOP, is simply a pointer that points to the header of an object, and this header explains how to manipulate the rest of the object. So in this case, very simple object that has 3 slots, and each slot contains another OOP. So this is again a pointer to a header somewhere else in memory. And to illustrate why that might be complicated, let's take a look at compiled method. So compile method, the first is always the header as it is for every object, but the first slot actually is not header. It's not an OOP, it is an extra header. This is a very big integer. Then you have literals, which are OOPs, which is good. So you can iterate over them normally. You just have to add a +1 at the start. But at the end, you have bytecodes. So a bytecode is actually 8-bit indexable. So you can have between 1 and 8 bytecodes inside the 64-bit integer. And therefore, you cannot iterate as you would do for other things. But the number of slots by the VM returns all of that information. And therefore, you have to, when you want to iterate over the slot of a compile method, you have to take into account that you have extra header, you have a bytecode that you cannot iterate that which are not OOPs. So this complicates how you manipulate that memory structure um, directly. And the other thing is that the bytecode, as I said, it's between 1 and 8 bytecode inside 64 bits. But what is the order? Where is the last bytecode? What is after that last bytecode? And all of these questions you have to answer before you are able to manipulate this data structure and this bytecode. So, to continue with an example also from the paper, is I want to find a class which has a specific name. Don't go through in depth of the snippet. This is not the point. I just want to give you an overview of this. So first, you have to iterate over the classes that were registered inside this environment. So you have to use the class table entries do, and then you have to get the class name index for a given OOP, which depends on whether this is an OOP, a class OOP, or a meta class OOP. And meta classes do not exist actually at the VM level, as you can see in the paper. And then you can finally get that OOP by fetching a pointer of the class OOP that is as argument. We can convert the string OOP to a string object that is of the host environment. And finally, we are able to compare whether this is the class name that we want. And if no class has that name, then we return nil or null for other language. If I execute this inside a given environment, I got 400 million something, and this is an OP, this is an address, but this is very difficult to work with. Did it return to me nil object, or did it return the actual class form? I'm not sure. Did it return something else? Is there a bug? I don't know. And this is why we try to ease that process. So to highlight what is a bit different with what Pharo developer usually encounter. First, Pharo developer works with objects. This is an object-oriented language, and therefore they are not used working with addresses with OOPs. This is usually also a low-level style, so the memory knows everything, and you have to query the memory for everything that you want to check. And finally, this is an OOP-based API, so the memory knows everything, but depending on OOPs that are provided as argument. And the thing is that if you give the wrong OOP, the wrong kind of OOP for a particular method, this will not work, or this will create an error or something. We don't know what happens. And one thing that I ignored initially is that the class table entries do is using the class table, which is a VM level entity only. Pharo developers do not know that it exists. So this is a bit of a big knowledge gap to jump through when you are a Pharo developer that wants to go and try to do stuff on the VM. It can get a bit disparately very quickly. So to summarize, the issues that I'm pointing at is that we have ordinary object pointers rather than objects. We have an API that manipulates all OOPs regardless of their kind, and this is only VM level information. It doesn't know how the language that is running on top of the VM works at all. And introducing our solution, so language level ordinary object pointers in a solution that we called Polyphemus. So as I said, instead of using OOPs, we are using language level entities. So in the case of Pharo, objects. Then we are identifying and typing OOPs rather than keeping them as void star. And we are merging VM level and language level information to be more precise about the kind of things that we have. So first, to do that, we have to iterate the memory. We have to look at every OOP. So to do that, the usual way is just to take the address of a first object. You add the size of this object to the OOP, and then you have another address which should be the next OOP. You do that so on and so on, and you get to have all of the OOPs. And the question that you want to ask to each of them is, what are you? Are you a class that is known at the VM level? Are you a meta class, which is not known at the VM level, only at the language level? Are you a free object, which is only at the VM level? Are you something else? No? Okay. If you have no particularity, you are just an instance of a class. Good. So by applying this process, we can type the OOPs. We get a language level OOPs then that we put inside an identified memory. The point is that rather than having tools that are manipulating OOPs directly, they are manipulating an higher level entity, that is in the case LLOOPs, and the identified memory may cache or not these OOPs, depending on the kind of tool that you want to write. So here I have a little snippet of code that is representative of how I write tools at the VM level now. Like you can see that I'm asking my refined memory, all classes OOP. I don't care anymore about the class table. I'm only wanting the classes OOP. I want maybe the refined meta class. Maybe I want all the class side, so the meta classes of the classes that exist. Or I can write more complicated stuff, like taking all of the objects, getting the ones that are compiled method OOPs, and then collect for each of them the decompiled version of that method. And if there is an error, I have a catch that does nothing. The point of this is that I'm writing Pharo code now. I'm not writing VM code. I'm writing Pharo code for a specific application that is the VM. But this is Pharo code that can use try and catch, which I couldn't use before, etc. And from that, we have done a lot of stuff, small stuff that are, for example, inspectors. In Pharo, we have a lot of inspectors that we can customize. So in the case of compile method here, I have VM level information only, such as the address, such as the OP class tag, the format. No, the format is not. This is both VM and language level, etc. I have also language level information, such as the method class or the selector, and each of these slots is named such as it just like they would be at the language level, which is nicer to read than just an address on which you would have to query every single one of these lines. Then you have the bytecodes and you have the literals. We will come back to this in a little bit. Another thing with way too much green, I should have turned it down a bit, is memory visualization. Many people have said that it reminds them of early Windows days with memory visualization. I think that's why I kind of like this green. It reminds me of something I didn't know why, but now I know. Point is that each box is now an OOP. And I am able to visualize this memory that is about 3,000 entity and look at it and wonder what some stuff on it. Particularly, if I'm scaling each box by the size that they take in memory, I get this drawing. The things that are important here is that we have a lot of boxes, but we have actually 4 that are very big here. And the thing is that this particular image was done to try to run Pharo in IoT, and therefore the image size was supposed to be as small as possible. And the thing is that actually, upon investigating a little bit more, these are class table pages, class table, and remember set. The point of these entities is that they are VM level only. The Pharo developers do not know about them. And the thing is that with this drawing, we can see in 1 second that if someone else wants to go back to this image and make it even smaller, the point is not to do it at the language level anymore. This is a VM level issue now. Another thing that we found was that we have a special object that is used between the VM level and the language level, which is the special object array actually. And it is expected to be at the top of the memory, at the start of the memory, because it shouldn't be garbage collected. But the thing is that in this specific memory, it is at the end of the memory. And the thing is that if it gets garbage collected for some reason, everything crashes because the VM expects it to find to not garbage collect it actually. So we found this bug and reported it thanks to something thanks by simply by naming the special entities that are known at the VM level. Another kind of visualization that we like in Pharo is a class a class browser. Which means that we look at all the classes that are loaded in the current environment, and we look at the method that we want to change. And in this case, for example, we found the class form, and we looked at this method, and we found the method that was initially broken earlier, right? And this took us 40 seconds to run. I mean, that's a lot faster than having to look at all of the OOPs and finding the links between everything. That's a pain. So the thing is that this error is actually called a meta error. So imagine that you want to compile a method, and actually the environment says, no, this doesn't work because there is a bug in my debugger. This is a method, an error that is unrelated to the initial problem that you were trying to achieve, but prevents you to achieve that initial action. Okay, so when we investigated this, we find a bytecode that has 3 more bytecodes than the bytecode of the method without this alt. So we can extrapolate from that this is the message send of the alt message to the self receiver. So first thing is that we have to remove them. Okay. Next, the literal one here on the left is with the alt version, of course, shows us that we have to have a literal that contains the name of the message that we will have to send in the method, and in the clean version, it is not there. And this is why we have a +1 offset between those bytecodes. So a thing that we have to do is remove a literal, remove the first 3 bytecodes, and this should work, right? And it did, actually. And what is important to know about what we did is that it took us about an hour to fix this, and 45 minutes was about loading the image inside the simulator, and we didn't know much about bytecode at the time. I mean, how the Pharo bytecode works. So it was fairly easy to do with little knowledge, and particularly, I didn't use any VM level knowledge to fix that. All I did was using Pharo level knowledge and apply it at the VM level. And I didn't have to care for all of this stuff of order of bytecodes, slots, etc. I just had to know to try to do some stuff. Okay, I don't have too much time, so I will accelerate a little bit. So the next thing is that we had to investigate the corruption, memory corruption. So in that case, we cannot iterate over all of the object. At some point, we get a corruption and says, okay, there is nothing after that point. The thing is that this is not true. There is a lot of stuff, but we don't know how to get them. So to do that, we try to recover as much object as we can, and we iterate over all of the slots of all of the objects and try to get to parts that are not corrupted, which gives us a memory like this. So we have actually tracked the corruption and isolated this corruption to minimal points inside this image. And we just this corrupted, and we can carry on with the execution, even though this is sorry. Even though this memory is corrupted, the thing is that we can carry on and recover the work that was previously lost. And the thing is that Polyphemus in this case didn't help that much at the. We had to touch VM level stuff, which are very precise, but it still helped us with object slot iteration and reference patching, particularly, and focus on learning how this corruption was working rather than having to figure out how to touch every object. So, in conclusion, tooling at the VM level is pretty difficult, and language level language level ordinary object pointers help bridge those knowledge gaps. With language level entities, identifying and typing OOPs, and by mixing language and VM level information. and I'm taking advantage of this situation to just mention that I'm looking for a job now. I'm defending my PhD in about 2 weeks now. And that's about it. Thank you for your attention, and I think we can move on to questions now. Thank you.
Do you have any questions in the room? Okay. Jeremy?
Can you try to speak very loud? See if Pierre is hearing you, otherwise we'll hear this.
Can you hear me, Pierre?
Yes, I can. Hi.
Oh, good. I'll shout. Thank you for your talk. I liked your nice graphical visualization of the memory.
Thank you. I get that a lot.
It reminds me a little bit of the old GC SPI framework, which Richard put together. Now, he imposed the heap structure in his framework, so you could see where the different generations were. Yours seems just to be a flat memory layout, or is there some structure that you'd impose on top of that? Thank you.
Oh no, this is very malleable. The thing is that we just tried to do it for fun because actually we didn't. We just did that for fun and it ended up in VMIL'. And this is not that useful, so we didn't work that much on it. But we have worked toward to have queries to be able to change how it visualizes, and to provide multiple ways of coloring the memory, multiple ways of displaying it, either with boxes or over stuff, to be able to have more customization option. But since nobody has used it that much yet, we didn't focus too much on this. We have tried more some fun stuff like recompiling with the decompiler of the host image. Stuff that shouldn't work at all, but apparently kind of do. Does that answer the question okay?
Thank you.
Okay, cool.
Any other questions? So I have a quick one, just to make sure I understand correctly. So you're looking at your own image, or you're looking, so you're running that inside a virtual machine and you're looking at your own image, or you're looking at a different image that you're loading?
I can look at any image. The thing is that the image is a static representation of a memory, and while the memory was uploaded, while the image is interpreted by the virtual machine, it is only at the start that it's uploaded in memory. Therefore, the file is still available to use at any point. So you can use, you can look at your own image, or you can look at any other.
All right. So when you're looking at your own image, are you looking at the running image or a static copy?
Sadly, currently a static copy. I would love to go for a dynamic. We wanted to, but this is slightly more complicated.
Yeah. Okay. So that would have been my next question. How do you keep things in sync when you have the garbage collector moving things around? So I saw you have pinned objects in there, and I was wondering, I assume that means you have a moving garbage collector, and how that.
Yes, we have actually. We have a mark and compact collector. And the thing is that if we were to finally be able to work on this and try to get the memory that is in RAM, the first thing that we wanted to do was to stop the world, basically, copy all of the objects inside the current environment, and resume. So we would work exactly like a GC, stop at a good point, at a safe point, and then carry on.
All right. So I think there is an online question, and I think so from Dave. He also asked, "Is that all offline?" And I think you just answered it. So at the moment, it's all offline, right?
Okay. I do not see it, but
yeah,
might be in the wrong thing.
Do you have any other questions in the room? All right. Then let's thank Pierre again.